Hello my dear students. In the previous session we have learnt the structure of an eye and understood how the image formation takes place in our eyes, and also we have learnt the different defects of vision and how do we correct them. In this particular session we are going to understand the refraction of light through a prism and dispersion of this light through this prism, and also we are going to learn the atmospheric refraction and also the scattering of light. Yes, let's get started. Now before going to understand the refraction of light through a prism, we have to understand what do we mean by prism. Basically, this prism is an optical element which is three-dimensional in shape, and it consists of at least two plane surfaces with an angle between them. This is the most commonly used triangular prism. So, prism is an three-dimensional optical element having at least two plane surfaces with an angle between them. You can see here, this is the most commonly used triangular prism. Why it is called as triangular prism? Because it consists of two triangular bases and three rectangular lateral surfaces. This face what you are seeing here, it is triangular base, and in the opposite side also we are having the same triangular face, and on the sides you are going to see here these are rectangular surfaces, and below also we are having the rectangular surface. So overall this triangular prism consists of two triangular bases and three rectangular lateral surfaces, and between these lateral surfaces there is an angle between these two surfaces, and this angle is called as angle of prism. Yes, triangular prism, it consists of two triangular bases and three rectangular lateral surfaces. These are the triangular surface. On the back side also we are having one more triangular surface, and by the side you are going to see here the rectangular surfaces on this side and on this side, and also at the bottom of this prism also we are having the rectangular surface. So overall we are having two triangular bases and three rectangular surfaces. This is about the triangular prism. Now we are going to understand how does the refraction takes place through this triangular prism. And I have said that this angle between the two lateral surfaces is called as angle of prism. It is an angle between the two refracting surfaces. Now we are going to understand how does the refraction takes place through a glass prism. We have understood the phenomenon of refraction through a rectangular glass slab in the previous chapter. In that case, the two refracting surfaces were parallel to each other. In that case, we had got an emergent ray which was parallel to the incident ray, and there was lateral shift there. Now here we are going to understand the refraction through this prism where there is an angle between the two refracting surfaces. Yes, this ABC is a triangular glass prism. This is an incident ray. This PE is an incident ray. You can see here, this is a normal to this refracting surface, that is N dash. Now, as the ray of light enters from rarer medium to denser medium, it is traveling from air into the glass, that is from rarer medium to denser medium. Then how does the light bends? It bends towards the normal. So, it gets refracted along this line. This EF is refracted ray, and this ray makes an angle R with the normal, that is called as angle of refraction. Now as this ray of light, that is refracted ray of light, falls on this surface, again it is going to enter from one medium to another medium, that is from denser medium to rarer medium, and this is the normal at this point. See here, after getting refracted, this ray of light will bend away from the normal, because now it is moving from denser medium to rarer medium. This is the normal here, and this light ray is refracted away from the normal, and this Fs is called as an emergent ray, which emerges out of the prism after getting refracted. So it has undergone refracted twice here, when it was moving from rarer to denser medium, and again when it is moving from denser to rarer medium again. And this ray, which is called as emergent ray, is making an angle E with this normal, and this angle is called as angle of emergence. And also see here, in the absence of this prism, the light ray would have traveled along this way, because there was no change in medium in the absence of this prism. Now, in the presence of this prism, it has got refracted in this way. Extend this line towards here. You can see here, this is an angle made by the emergent ray and the incident ray. This angle is called as angle of deviation. It is very important to know the angle made by the emergent ray with the incident ray. The angle between the emergent ray and the incident ray is called as angle of deviation. Yes, now let's write all these facts here. This PQ, PE is an incident ray, and EF, which get refracted towards the normal, and EF is a refracted ray, and this FS is called as an emergent ray, as it emerges out of the prism of the refraction. Now this I is an angle of incidence, that is angle made by the incident ray with the normal. I is an angle of incidence. And this angle which is made by the refracted ray with the normal is called as angle of refraction. And this angle which is made by the emergent ray with the normal is called as angle of emergence. Now this is the angle of prism. As I have already said, the angle between this emergent ray and the incident ray is called as an angle of deviation. Now you have observed the difference here. In case of rectangular glass slab, the emergent ray was parallel to the incident ray. Whereas here, these two are not parallel. This is the incident ray and this is the emergent ray. There is an angle between these two rays, that is called as angle of deviation. Interesting and exciting phenomenon was found out by the scientist Sir Isaac Newton. He found that whenever a white ray of light is passed through a prism, it was split into 7 different colors. And this phenomenon is called as dispersion of light. He found this phenomenon around 1666. What he done was, a white ray of light was passed through the prism. White ray of light. When it is incident on the prism, it had got refracted and it is split into 7 different colors, and these colors were found out to be violet, indigo, blue, green, yellow, orange, red. And always the same sequence was followed. Red color was always obtained on the top and violet color was always obtained at the bottom. And these band of colors which are obtained, they are called as spectrum. The band of colors which is obtained when a white ray of light is passed through the prism is called as spectrum. And this phenomenon of splitting of white light into its constituent colors is called as dispersion of light. This shows that white light is made up of 7 different colors, because of which it has got split into different colors there. So what do we mean by spectrum? It is the band of colors obtained by dispersion of white light. The light which is coming from sun is white light. When we pass that light through the prism, it is split into 7 different colors and we call it as dispersion of light. And here the question arises, why does the dispersion takes place? It is due to the fact that different colors bend through different angles with respect to the angle of incidence. You can see here red color bends the least. Red color, it bends the least. And you can see here violet color bends the most. Violet color bends the most. And also note here that the different colors have different wavelengths. That is the distance between the two consecutive crests or curves is called as wavelength. And also different colors have different wavelengths. The color which has longer wavelength will bend the least and the color which has shorter wavelengths will bend the most. See here red color has longer wavelength and it will bend the least and violet color has shorter wavelength and it will bend the most. So wavelength means it is the distance between the two consecutive crests or troughs. As the wavelength increases, the bending becomes less. So wavelength and bending are related inversely to each other. More the wavelength, less is the bending. Less the wavelength, more is the bending. So wavelength is inversely proportional to bending. This shows that red light travel with more speed when compared to the violet ray here. And violet ray travel with less speed out of all these colors. So it is bending the most. Among all these colors, red light is having the maximum wavelength, so it bends the least. And among all these colors, violet is having the shortest wavelength, so it will bends the most. This is all about the dispersion of light through the glass prism. Here the question arises, when the white light is going to split into different colors, then is it possible to combine all these colors and can we get the white color? And the answer is yes. Because it is due to the fact that white light is composed of 7 different colors. And to make this discovery strong, again Newton had gone through one more experiment here. That is about the recombination of the dispersed light. When the recombination of the spectrum of white light was done, they produced the white light. This shows that the white light is made up of 7 different colors. See here, this is a white ray of light which is passing through the prism. And after getting refracted, here you can see it has shown the dispersion here. It is split into 7 different colors. For the sake of convenience, we have shown here only the 2 colors. There are still 5 different colors in between. And as the spectrum of this white light which is obtained here, it was passed through the another prism which was placed in the inverted position. Remember, this prism is in the erect position and this prism is placed in the inverted position. So, all these colors were combined to form here the white light. So, this made the statement strong that white light is composed of 7 different colors. If the white light was split because of the prism only, then it would not have happened here. These colors would have not combined to form a white light here. It is due to the reason that white light is composed of 7 different colors. It is again combined into a white light when this prism is placed in the inverted position. You can see here the refracted ray will always bend towards the base here. In this case also, in this case also, you are seeing here when the spectrum of colors were passed through the prism which is placed in inverted position, it is also bending towards the base here as it is in the inverted position. So the recombination was taken place to form the white light. So white light is made up of 7 different colors, that is violet, indigo, blue, green, yellow, orange, red. Now we are going to understand the atmospheric refraction. We have already studied that refraction means it is the bending of light when it travels from one medium to another medium. Here we are talking of atmospheric refraction. Whether the refraction also takes place through the atmosphere? The answer is yes. It is because of the fact that the atmosphere is composed of different layers, and all these different layers have different optical densities, because of which whenever the rays are traveling through these layers they undergo refraction. And this refraction which we see in the different layers of the atmosphere, it is called as atmospheric refraction. Our atmosphere is made of different layers of different optical densities. As ray of light passes through these layers, they undergo continuously refraction. They undergo continuous refraction. So this type of refraction that occurs in the atmosphere through different layers is called as atmospheric refraction. By the concept of this atmospheric refraction, we are going to understand some facts here. The first is twinkling of stars. We have to understand what do we mean by twinkling. We know that stars appears like sometimes very bright and sometimes dim. Stars, they appears continuously bright and dim. When they appear bright, more amount of light is reaching our eyes. When it appears dim, less amount of light is reaching our eyes. So as it continuously becomes bright, dim, bright, dim, bright, dim in this way, it appears like it is twinkling. Actually, the star is not twinkling here, but due to the change in the amount of light rays entering into our eyes, it appears like it is twinkling. So why does this happen? The answer is it is due to the atmospheric refraction. We know that this is our earth. It is surrounded by different layers, and all these layers have different optical densities. So the rays of light coming from stars, sun, they undergo continuous refraction here. And also in each layer again the atmosphere is not same. If here the density of the gases is more, here it may be less. Here it may be less again, here it may be more. In this way, the atmosphere is continuously changing. The best example is you might have seen the objects through the hot stream of air. It appears like those things are wavering or flickering when you see it through the stream of hot air. Why does this happen? Because the layer of air just above the fire, it is very hot when compared to the layer above it. And because of being hot, it becomes less denser. And the layer above this air has the air which is cool and it is more denser. As the rays of light travel from less denser air to more denser air, what happens? The refraction is going to take place. And those refracted rays will reach our eyes, because of which the object will look from the different position. And this atmosphere is not stationary, it is continuously changing. Because of that, the refracted rays will reach our eyes from different positions. So it looks like as the object is continuously flickering or wavering. And because of this atmospheric refraction only, the stars appears like they are twinkling. See here, this is a star, actual star which is present in the sky. The rays from it are coming and those rays will undergo continuous refraction as it passes through different layers of atmosphere. And it appears for this person like those rays are coming from this point, because it has undergone refraction here. Bending of light has taken place through the different layers of earth atmosphere. And again the earth atmosphere is continuously changing. Sometimes the refraction will take place in different way. It may be taken place as like this, and this ray looks like as if it is coming from here. And sometimes the refraction may take place like this, and it may look like as if these refracted rays are coming from here. Because of the continuous change of atmospheric conditions, Sometimes even in this layer itself, some place has more density, some place has less density, and in other layers also the density of the medium will changes. So the refracted rays will reach our eyes from different positions, slightly different positions. So it appears like these stars are twinkling. The apparent position of these stars will change continuously. Sometimes more amount of light will reach our eyes, sometimes less amount of light will reach our eyes. Because of that, they continuously seems like bright and dim. And this star acts like point sized object, that is point sized source. Star, it acts like point sized source because it is present at a very larger distances, so it can be considered as a ray here. Because of that, here twinkling of stars takes place. Actually the stars are not twinkling, but it appears like as if they are twinkling. See here, the twinkling of star is due to atmospheric refraction of starlight. The starlight, when enters into the earth's atmosphere, it undergo refraction continuously before reaching the earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, you can see here the ray is bending towards the normal because it is entering from optically rarer medium to denser medium. The atmosphere near the earth is very denser when compared to the layers above it. So, the apparent position of the star is slightly different from the actual position. The star appears slightly higher, and you can also see it appears slightly higher above than its actual position when viewed near the horizon. Further, this apparent position of the star is not stationary, and again when you see the star from this position, it is not stationary. Again the refracted rays may reach your eyes from different position, from here or here, because of which it will seems like they are twinkling. So the path of rays of light coming from the star goes on varying slightly. The apparent position of the star fluctuates and the amount of starlight entering the eye flickers. It continuously changes. Amount of light entering your eyes is continuously changing. Because of that, the stars appears twinkling. And now the question arises, why do planets do not twinkle? It is due to the reason that the planets are nearer to Earth when compared to stars and they appear big. Now they are not considered as a point sources as in case of stars. They are considered as a extended sources of light. See here, planets, they are nearer to us. They appear big. So now they appear as extended source of light. And also it is considered now as a collection of large number of point-sized sources. Collection of large number of point-sized sources. So, as these planets are considered as collection of large number of point-sized sources, what happens is the different part of these planets will produce either brighter or dimmer light, and in such a way that the average of the brighter and dimmer effect is cancelled to zero. Hence, the twinkling effect of the planets are nullified and they are not twinkling. But in case of stars, what happens? The starlight is refracted by the atmosphere and comes towards us. Sometimes it comes more towards us and sometimes it will be reaching in a lesser amount, because of which it will appear sometimes dim and sometimes bright. So it appears like they are twinkling. So the different parts of the planet produces either dimmer or brighter light in such a way that the average of brighter and dimmer effect is nullified. This is the reason why planets do not twinkle. Now we are going to understand about the advanced sunrise and delayed sunset, and again it is due to the atmospheric refraction. See, this is our earth and a person is standing on the earth here. Horizon means it is an imaginary line where sky and earth appears to meet, and we can see those objects only which are above the horizon, and when an object is below the horizon we cannot see that object. Even in the case of sun also, when the sun is below the horizon we are not able to see it, and when it comes above the horizon we say the sunrise has taken place. Now the sun is about to rise here. This is the sun. It is about to rise. So it should not be visible to our eyes. But what happens here? The rays coming from the earth. But what happens here? The rays coming from the sun when reach the earth atmosphere, which is made up of different layers of different densities, it undergoes refraction here. It will undergo the bending, and those refracted rays will reach our eyes, and it seems like this ray is coming from this point, and we have learned that from which position the refracted rays will reach our eyes, that position image is formed. So a person sees the sun here. It is not actually the sun, it is apparent position of the sun. And after 2 minutes, we are going to see the actual sun there. As sun was visible to us before 2 minutes of the actual sunrise, it is called as advanced sunrise. It is due to the atmospheric refraction. So, the same phenomenon can be applied for delayed sunset also. The sun is visible to us even after sunset. About 2 minutes, the sun is visible to us. This is again due to the atmospheric refraction. The sun is set actually, but it will be visible to us because again it due to the atmospheric refraction. When it reaches the earth, it undergoes refraction. After undergoing refraction, what happens here? For an observer eye, these rays appears like as if they are coming from this point. So still the sun is visible for about 2 minutes even after the sun is set. It is due to again atmospheric refraction. Now we are going to understand one more phenomenon of light here, that is scattering of light. Whenever the light hits any particle, it will scatter in different direction. Whenever the light rays coming from the sun hits the particles present in the atmosphere, because our atmosphere is made up of many particles like dust, smoke, tiny water droplets, many other gases. So the light coming from the sun hits the particles of atmosphere. What happens here? Once it hits the particles, this light is scattered in different directions. This phenomenon is called as scattering of light. And we can see many examples for this scattering of light. The very known example is Tyndall effect, which you have studied in grade 9. What you have learned there? When the light is passed through the colloidal solution, the particles present in the colloidal solution will scatter the light in different directions, and because of that the path of the light is visible, and this phenomenon is called as Tyndall effect. See here, see here, when the beam of light coming from the torch is passed through the true solution, where the path of the light is not visible here, whereas the same beam of light when it is passed through the colloidal solution, here the path of the light becomes visible. This phenomenon is called as Tyndall effect. Here the size of the particles matter. The scattering takes place when the size of the particles is more than 1 nanometer. Here, in case of true solution, the size of the particles is very less than the 1 nanometer. So here, the scattering is not taking place. This phenomenon is called as Tyndall effect. If the light is passed through a colloidal solution, the particles scatter light in all directions and the path of the light is visible. This phenomenon is called as Tyndall effect. You can also see the phenomenon of Tyndall effect in the canopy of forest, where it consists of large number of tiny water droplets or mist. What happens there? When the sun rays hits those tiny water droplets or any other mist particles, the light is scattered in different directions, because of which you can see here the path of the light becomes visible. It is due to the Tyndall effect. This is the most familiar example of scattering of light. The blue color of the sky can be explained based on the scattering of light. One thing you have to understand in the scattering of light is the color of the scattered light depends on the size of the particles. What happens usually is very fine particles, they are effective in scattering the light of shorter wavelength, whereas larger particles, they are effective in scattering the light of longer wavelength. We know that our earth is made up of the atmosphere, which contains the molecules of air, and these air particles and other fine particles, they have size which is smaller than that of wavelength of visible light, because of which they are effective in scattering the light of shorter wavelength like blue color. Which colors are having shorter wavelength? Violet, indigo, blue, they are having shorter wavelength. And these particles, they scatter the light of shorter wavelengths here, because of which blue color will reach our eyes. And here the question arises, why not violet and indigo? Because for these colors our eyes are not sensitive, so only blue color will reach our eyes. Understand here, very fine particles, they scatter light of shorter wavelength, and large particles scatter light of longer wavelength. And we can say the shorter wavelength light is scattered more easily than the longer wavelength. See here, the molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of visible light. So these are more effective in scattering light of shorter wavelength. Which colors are having shorter wavelength? We have violet, indigo, blue colors, which are shorter in wavelength at the blue end, then light of longer wavelength at the red end. And the red light has a wavelength of about 1.8 times greater than blue light. Thus, when sunlight passes through the atmosphere, the fine particles in air scatter the blue color, which is of shorter wavelengths, more strongly than red, because of which this scattered blue light will reach our eyes and the sky appears blue. Here the question may arise, what happens if there is no atmosphere? Then absolutely correct that sky will appear black. This scattering of light is caused by the atmospheric particles. If there is no atmosphere, then the sky would appear black in color. And it is for this reason that astronauts will see the sky as black color, because there is no atmosphere there. And again, when you go into more higher altitudes, what happens? The sky will appear black, because no prominent scattering takes place there. Here, one more application of scattering of light is the danger signals are given the red color. Why? Because we know that red color is least scattered, and it can be seen in that color only even if you watch it from distance. Red color is least scattered because it is having longer wavelength. More the wavelength, less is the scattering. Lesser the wavelength, more is the scattering. In this way. So, it can be seen in the same color even at a distance, because of which the danger signals are given the red color as it is scattered least. This is all about the chapter Human Eye and the Colorful World.